So now let's talk about a bigger picture of deep learning, right? A bigger picture, because if you think about, where it's coming from, right? Right. So we got to think bigger than just the feed-forward neural network. So what else can we do, right? So deep feed-forward neural networks, or MLPs, opened the Pandora's box of deep learning in the early 1990s, and their training became practical in early 2000s, right? Backpropagation. Right? Remember, that was not apparent when Minsky wrote the book in 1969 critiquing, not criticizing, critiquing the perceptrons, right? Those algorithms were not known, right? We know that they were actually available, but just not known. Until 1986, and we know that, there are a lot of articles about the real history of backpropagation, but that aside, right? Another thing I want to say that MLPs are often used for tabular data, right? It's like a table format where each row is an example and each column is a feature, right? So in other words, there's not too much structure, right? You can swap the rows, it doesn't matter, right? Because each row is an example. You can swap the columns, doesn't matter because each column is a feature. There's no order among the examples and there's no order among the features. So there's not a lot of structure, right? So for this kind of tabular data, there's not a lot of structure, and MLPs are often used. And actually, if you look at the Kaggle competition, whenever there's tabular data, right, the frequent winners are random forest and XGBoost, right? So not very surprising, right? But then we see that in the image or text, there are more structures than tabular data. Then we can talk about how to utilize the structures, okay? So what else? As I said, the first example is image data, right? So what are the image data, right? So image data are actually very interesting because they are discrete samples of continuous signals. You see what I mean, right? In nature, right, these are continuous, right? But when I take a picture of the continuous object, I can only have a discrete sample, right? For instance, 800 by 600 image, right? Meaning that I have 800 pixels each on the width and on the length and 600 on the width, for instance. So I have 800 times 600 pixels arranged on the grid, right? Two-dimensional grid. So these are what image data are. So apparently this is very different from the tabular data, right? Because there is order between rows and columns, right? And for each grid, right, out of 600 times 800, I can give one or multiple numerical values, right? For instance, if it's a grayscale between 0 and 1, or it could have RGB, 3 values, right? Red, green, blue, right? Or CYMK, right? In printer, right? Sometimes they use CYMK, right? Cyan, yellow, magenta, and black, right? And for each color, or later you will see that they are called channels in neural networks, right? There is a single numerical value for each color or channel. So now we understand that, well, this is what image data are, right? So 2D grid, each grid with one or multiple numerical values. So now, what if we treat images or photos as tabular data sets, right? Well, each row of a megapixel photo can be flattened, okay? So instead of 1 megapixel photo, right, is, for instance, 1 megapixel, for instance, 1,000 by 1,000, okay? So what if I just flatten the rows, convert this 2D matrix into a 1D feature vector, right? Row by row. So I have 10 to the power of 6 dimensions, right? And then I just feed this 10 to the 6th dimension feature to the MLP, right? So this is, if we just treat image data as tabular data. So can I do that? Well, of course you can do whatever you want, but do you see the consequences? Is that something you like to see or not? What are the consequences? Do you like to see this consequence or not? I see someone shaking heads. Ryan, any comments about this approach of treating image data as tabular data and use MLP to learn the image data? The order in the image is important. That's one source of information. Yes, and I more or less respected it. That within each row I kept the order, just also across different rows I also kept its order. The only thing that artificial is that, between the last grid of the previous row and the first grid of the current row, I introduced something artificial. Is that right? But no matter what I do, MLP does not really utilize that order information. Not to mention that I introduced some artificial order, right? MLP does not care about such order information. These neurons are interchangeable within each layers, right? Okay, that's one critique. What others? So your critique is saying that the structure of the image data is not utilized. Any other critique? Look at this number, 10 to 6. How many input neurons do you need? 10 to 6. Is that something you desire? Probably not. Right? So let's say you have one hidden layer with 10 to 3 neurons. How many parameters do you end up having? How many parameters? You only have one hidden layer. Okay, input layer has 10 to 6 neurons. Hidden layer is 10 to 3, small, okay? And the output, let's say you're doing the binary classification, whether it's a cat or not. So let's just say there's a single O. So how many parameters do you roughly have? What's the dimensionality of your W? Huh? Multiplication of between 10 to 6 and 10 to 3. So that's the number of edges here. Is that right? Plus this multiplication of 10 to 3 times 1, but that's much smaller. So it's order of 10 to 9 times some constant because there's bias as well, right? But it's in the order of 10 to 9, right? So for just a megapixel photo, right? You need the 10 to 9 model. That means what? To train this extremely large model accurately, you need a lot of data, a lot of GPUs, and extreme parallelization for optimization, right? You can do that, right? But it comes with a cost. So instead, right? So if we conclude that MLPs for image data are extremely complex models that demand data and computing, then what do? We learned before that, if your data is not something you can change, right? And your model is too complex for the given data, you have to control the complexity or regularize the complexity, right? So how do you regularize MLPs in this case? In other words, how do you change MLPs so that it works for the image data? Right? So to answer that question, let's go back to the biology and ask, how do our vision system works so well? Right? Our vision systems works so well. How do they work? Can we emulate that and then regularize or change our MLPs accordingly? So that's a question, right? Right? Because we cannot just pat our heads and they come up with a new architecture. You see what I mean? So this is one example, right? How our vision systems work. This is our target called Waldo. Okay. Well, I'll give you 1 minute to tell me where Waldo is in this image. Let me move away this to be less distracting. Okay, you gotta pay attention to the pattern of the target and ask yourself, what's the best way to search, right? You are actually having a neural network in your brain now, which is being trained previously, right? Now you're transfer that neural network to identify Waldo. Where is Waldo? Any luck? Let's give it another 30 seconds. Anyone with success? I remember last year it was Randy who found it first. Some of you know Randy. Okay, let's stop here. And the important thing is not about the answer, okay? The important thing is you rationally get aware of how your vision systems work. That's the point, okay? If you ask about the answer is here. Do you see it? Do you see him? Caught by the savage and bonded. See him now? Okay, so as I said, the answer is not about where is Waldo. The question is, how did our eyes and brain work together to find Waldo, right? Right? So there are a few things, right? So how did we really find Waldo, right? So first of all, right, there's got to be something, right? There's got to be something about the fact that the target is invariant to something, right? So in other words, it doesn't matter where the target appears translationally in the image, right? Or it's perturbed a little bit, right? And it doesn't matter. So there's something invariant to the transformations, in this case, translations or rotations, right? You see these red and white stripes and the heads, right? Right? And this part is known in the target, and it's invariant to where this image is, rotationally or translationally, right? And secondly, you're going to have to see through the destructor. In this case, he has been attached, he's bound with a lot of the strings, and then that is distracting you. You have to discriminate against such distractions, right? And then you will have to do something more efficiently. Somehow you have to figure out which blocks, and how do I search block by block, or how do I search, right? So this, and a little bit prior training, right? Because you have learned how to search for objects. But in this case, it's a novel object. It's Waldo, but then it's a little bit transferring from your prior to the new task, right? This is what we learned about how our vision systems work. So now let's translate it. So now, the reason that eventually we went from the dense layers to convolutions, right, is based on the two observations or knowledge about our vision systems, okay? First is that they respond to similarly to the same object, in this case, Waldo, regardless of where it appears in the image, okay? No matter where it appears, as long as our eyes see that pattern, it knows that it's there, right? So in other words, it's translational invariant, okay? So the output signal is invariant to the translation of Waldo's positions. Secondly, they focus on local regions without regard for what else is happening in the image at greater distances. So in other words, it's when finding this object, right, you very often, restrict to this locality pattern, right? Right? Where you need to find this small object, right? So these are the two observations: translation, invariance, and locality, right? So now is the question, if we want to emulate the vision systems, how do we translate these two knowledge into mathematics and regularize MLPs? If convolutions haven't been invented yet, how would you figure that out, right? So, before I give you the answer, right, I'd like to say that deep learning has so many different architectures as we know now. There's feedforward that is already introduced, but there's also feedback or bidirectional or recurrent neural networks, right? A lot of possibilities. And we talked about perceptrons and feedforward, and there are other possibilities, right? We talked